Okay, welcome back. So this topic is very important, and I wanted to make uh, uh, a deserving introduction to it. So what do we see in this figure over here is the pandemics that kill more than 2,000 people in today's population. So if there were less people when the pandemic happened, we rescale it such that we can think of it that if there was the same amount of people living in the world as today, what would be the estimated number of deaths for that pandemic event? So we see the years going towards 2020 is here, and we see the deaths caused by the pandemic on the vertical axis. We can see that most of the pandemics seem quite small in scale because this is in billions, this axis. So you remember that it matters what sort of an axis you choose. But these things called fat tails, you remember that we spoke about the body of the distribution and then the tails of the distribution where the extreme observations lie. So a fat-tailed distribution means something where there are observations very, very far out in the tail. So if you have a normal distribution, the tails, they stop very, very short, so to say, and it's practically impossible to have an observation that is sort of the 10,000 times the typical observation within the bounds of what's considered typical within 1 or 2 standard deviations, for example. But here you see that there are a lot of, so the typical event, one could say, is very small. And then there are a few, so maybe about 1% of the pandemics that kill more than 1 billion people if they end up killing more than 2,000. And so this is a problem if we want to think in terms of, so what's the average or the typical observation, because we can't just say that, well, let's just consider these observations outliers and not really care about them much. But if you would do that and you would crop the scale here, so now this is only in millions, and we say that nothing over 1 billion has, we ignore everything that's over 1 billion. So you see that the same shape of the histogram here still stands. So you have a lot of observations that are very small, and then you have these, so a couple of million, maybe 10,000 or something casualties. But then you have these that are still over and above 200 million. And if you compare and contrast this situation with one where we have the traffic deaths in Finland. So here we have the average line. So what's the average of the distribution? Here it's something like 20 million, because, but the typical observation is something like in the tens of thousands or something like this. Now, if we look at this axis, it contains thousands of deaths, and we have the average line. So if you were willing to ignore that in 1970s we had seatbelt laws and that started the road accidents started going down, it wouldn't be that bad of an estimate. A better estimate could be, if you wanted to condense it, you might use the mode, for example. But it wouldn't be that bad to think of an average number of traffic accident deaths in Finland. But what would be very, very weird is that if you would say that you expect that 1 year it could be that instead of 1,000 or 500 traffic accidents, we would have 100,000 traffic deaths. Because there's really just no mechanism for why that would ever happen. Whereas with the pandemics, it's quite clear and intuitive even that it's very possible for there to be an event that causes more than 100 or 1,000 or 10,000 times more casualties than a sort of typical event. And reasons for this have to do with global connectedness, interconnections, and we will speak about that when we discuss complex systems and risk management in more detail later in this course. And the interesting thing about fat tails and thin tails is that so let's say you rank each observation. So you have such that you have one, so each of these points is still 1 year. And so this is the year with least traffic deaths. And and this is the year with the second least traffic deaths. So you take their rank. And you look at how big a proportion of observations are bigger than this one, and you take the logarithm of that number. It doesn't matter for this conversation what the logarithm is. It suffices to think about the repercussions. And on the horizontal axis, you have the deaths, and you take the logarithm of the deaths. And what you see then in this log-log plot, is also called a ZIP plot, ZIPF, is that if you take only the 25% of observations that are in the tail, and you fit a linear regression to it, we see that with these traffic deaths, you see it doesn't really fit. It looks very stupid to draw a line that would describe the observations here, because taking the logarithm causes it to bend sharply downwards. And if we would take not 25%, but we would take the largest 10%, 5%, 1% of observations as we collect more and more years, then with these thin-tailed distributions, what you would end up seeing is the best fit would be basically or with a Gaussian or a normal distribution, the best fit would be a vertical line. But here, with the fat-tailed variable, with the pandemics, it actually fits quite nicely. And the thing about this is that if we would wait 100 or 1,000 years, the number of pandemics that we would observe that would be extreme pandemics, they would fall somewhere, or they could fall somewhere along this line. And so if there was an observation here, the line would slope even more towards a horizontal line instead of a vertical line. And this gives us an indication of what kinds of observations should we expect. So what kinds of extremes should we expect? In the case of traffic deaths, what we can expect are the extreme events that we can expect are likely to be very much like the previous extreme events. and sort of so there's almost like a gravity that pulls them towards the average. Whereas with the fat-tailed variable, with pandemics, for example, or cybercrime or terrorist attacks and so forth, what the extreme event that we are that we should expect is even larger than the most extreme event that we have seen thus far. So it's not like we should prepare for the last biggest event, but we should prepare for actually a much bigger event, because the existence of that prior largest event, it only stands to prove that even bigger events are possible, because we have this what's called the law of regression to the tail. So if you've heard about the law of regression to the mean, then Flubia has this paper called Law of Regression to the Tail, where he explains this phenomenon. So in the case of fat tails, expect even worse to come. And in the case of thin tails, expect something similar to come in the future. And one sort of distressing feature of these distributions is that if you take a normal distribution and you start adding variance, it doesn't compound equally. So you might not get a less peaky distribution that's even more sort of looks like a molehill, but you would instead start getting a spike. So what I show here is there's a blog post with code on how to do this, and it's very nicely shows the intuition that comes that when the distribution starts flattening, you start seeing more and more ordinary events. So this fat tail distribution here in purple, that has a lot more ordinary events than the yellow one, which is the normal distribution. And you might think that, oh, actually this our situation is very stable here, so there's nothing much to worry, because all we get is the same kind of observations year after year after year. But what this also implies is that you have fatter tails, so you also have more observations in the tail. So you have a situation where nothing happens, nothing happens, nothing happens, nothing happens, everything happens at once. And that's sort of a problem that we delve into when we think about, move on thinking about how to manage risk and opportunity in organizations with our data machinery and all we know about physics reappraising research methods and analysis. And these are the references that I've been using during this video. Some of them are quite technical, but for example, this one, it's very, it would be important for many people to